I have explained the method of variation of parameters to find a particular solution, of non-homogeneous second order linear ODE yesterday. So this is so here is the equation. So this is I explained you the method. This is the method of variation of parameters. So this is the method of variation of parameters that I explained just to find the particular solution of this equation. So what we do is you consider the homogeneous equations. So assume that you have a solutions y1 and y2. So you have a linear combination of that is the general solution of the homogeneous equation. Okay. Then you vary these constants as a functions of x. You are looking for the C1 and C2 in such a way that this combination yp will satisfy the equation, given equation. So once you can fix the C1 and C2, that will be, you will find so that you found a solution, a particular solution of the given equation. So along with that, you add this yp with yh will give you the general solution. So the procedure I explained you. So you consider its derivative, you impose a condition that this part is 0, so that will give you one condition 1, and then you differentiate this yp dash after imposing this condition. So then you substitute them back into the equation, will give you second equation. So if you solve it, so you get C1 dash, that system of equations, if you solve it, so you see that Wronskian matrix. So if you Wronskian matrix you have, and the unknowns as C1 dash, C2 dash, and the right hand side is 0 and f of x. F is the right hand side function of the non-homogeneous linear ODE. So this if you can easily find the solution, you can invert this matrix, because that is 1 by determinant is the Wronskian, and then you invert it, this is what you will get. So this is what you will get as C1 dash, C2 dash. Once you get the C1, C2 dash, you can differentiate, you can integrate either from x0 to x by fixing x0 in the domain of the differential equation. You can have C1 and C2 like this, and then you put it together, you will have this form, and that will be this form. So in a different way also you can do. So you can integrate directly as a definite integral also you can do. So C1x is simply minus integral y to x fx by wx dx plus C1. So let's say constant, call this d1. Okay. And similarly you can get either this or this. So either this or C2x also you can find as a definite integral. So y1x fx by wx dx plus some constant, integration constant d2. Okay. d1 is integration constant, and here d2 is constant, d2 is integration constant. So once you get them, you put it together. So either this form, or you will get yp as yp of x as c1x, c1x you know. So this is your y1x, and you have a minus sign for c1 y2x fx dx by wx plus y2x integral y1x fx dx by wx. So this is the form you have, either that or this, any one is okay. Okay, either this or this. So depending on the particular problem you do, you can use either a definite integration like this by fixing x0 in the domain, or indefinite integral. Okay, integration you can do as an indefinite integral, just to, if you know antiderivative of your integrand. So I have explained. So to calculate, so earlier example we have used x0. So in definite integration we can also do indefinite integral, so that you can get the same solution. Okay. So let us solve another example. So let us consider this, solving this equation in the domain x positive. So you consider homogeneous equation. So your homogeneous equation is satisfying this, but I know how to, this is the Euler-Cauchy equation, I know how to solve it. Okay. So x square y double dash, I have to put d square yh by dz square minus dy by dz, dyh by dz, this minus 3 x y h dash of x I can replace dyh by dz plus 4yh of z. This is a function of z with z equal to log x. This is the transformation, okay, x positive. Z is given as a transformation z equal to log x. So, this I know how to solve it. So, this will give me d square y by dz square yh, okay, and then you have a minus 4 dyh by dz plus 4 yh of z equal to 0. So, this is the equation. After with this transformation, you reduce this homogeneous equation into an equation with constant coefficient. I change by changing independent variable x to z. So, by letting your solutions function of z as e power lambda z, we get if you substitute here, you will get lambda square minus 4 lambda plus 4 lambda equal to 0. That will give me lambda minus 2 whole square equal to 0. That is nothing but lambda, you get repeated roots. So, this gives me my homogeneous solution. YH of z is C1 e power 2z plus, if it's because it's a repeated root, I will have C2 z into e power 2z. Okay. Now, I substitute z equal to log x, so that yh of z becomes yh of function of x, that will become C1, z is log x. So, you have x square plus and C2 x square log x, x positive. So, this is your general solution. So, y1 is what you have is y1 is, now this is your general solution of your homogeneous equation. This is one solution, this is another solution of your homogeneous equation. So, y1 of x is x square, y2 of x is x square log x. Okay. So, you look for yp of x, you are looking for c1x y1x by variation of parameters method. If you look for c2x y2x, that is x square c1x plus log x c2x. Okay. So, this is what you get, where c1 and c2 satisfies c1x c2x satisfies. What are those? We know what is c1x. c1x is nothing but minus integral y2. Okay. So, y2 is, what is your y2? So, this is what you have. So, you have this c1 is minus y2 fx by wx. So, what is you need a w also. So, wx is, you can calculate. So, determinant of this x square log x. So, if you calculate this 2x, this will be 2x log x, derivative is x. So, this will give me 2x cube log x plus x cube minus 2x cube log x. So, this gets cancelled. So, what you have is x square, x cube. So, you have wx is x cube dx, this will be c1x is y2. So, y2 is x square log x. Fx, what is your fx? Given equation, fx is log x. So, you have a log x square dx. So, this should be your c1x. What is c2x? c2x is integral y1. So, that is x square by wx is x cube log x is fx dx. So, this is, this you can replace. So, you will have this term. So, there will be log x square by x. Okay. So, you will have integral log square log x square by x dx. So, by putting log x equal to z, a new variable t, this will be simply integral t square, t cube by 3 is the answer. So, log x cube by 3. Okay. So, that is the integral value of this. So, that is your C1 of x, and C2 of x is, this gets cancelled. Okay. So, you have log x by x. So, this value is dx. This integral value, if you evaluate by the same technique, log x equal to t, by putting that you get log x square by 2. That will give you the integral. Okay. So, this gives me, now we go back and substitute into your particular solution. C1x is this, y1x is x square. So, x square by 3 log x whole cube, that is your C1 y1, and you have a minus here, I missed the minus. Okay. So, you have a minus plus C2 is log x whole square by 2 into x square log x. So, x square log x, that makes it 3. So, you have x square. So, you have finally, this is your solution. So, you have x square by 2, x square by 3. So, x square log x whole cube, this 1 by 2 minus 1 by 3. So, this will become 1 by 6. Okay. So, 1 by 6 x square log x whole cube, this is your particular solution. So, the general solution of the given equation is yx, which is C1 constant, arbitrary constant into y1 plus C2 into x square log x. So, this is your homogeneous solution. Okay. What is your homogeneous solution? So, this is your homogeneous solution I have written here, plus particular solution, that is 1 by 6 x square log x cube. So, this is your general solution, is the general solution. So, this is how you can solve this when you are having a linear equation with coefficients as Euler-Cauchy type, with the right hand side is log function. Okay. So, any function, for that matter any function. So, you can apply this method of variation of parameters, simply calculating C1 and C2 as given from these formulas here and here. Okay. Either of these, finally you can get your particular solution in this form or in this form. You can directly get your particular solution. When you add up with the homogeneous general solution of the homogeneous equation, you get a general solution of a given equation, because it has two arbitrary constants C1 and C2, and this is your solution. So, this is the general solution. So, as I said earlier, so you can solve non-homogeneous linear second order ODE. So, if you can solve, you can find y1 and y2. You can always find a particular solution by the method of variation of parameters. But if you are you don't have to do this method always, but when the right hand side, the non-homogeneous term is simpler form. Okay, when fx is in three combination elementary functions, okay, combination of elementary functions like polynomials, exponential function, or sine and cosine functions, then you can find a particular solution. You can find a particular solution by the method called method of undetermined coefficients. Okay. So, I will explain what is the method of undetermined coefficients. Okay. So, method of undetermined coefficients. This is just an ad hoc method that works only for certain when the function f right hand side non-homogeneous term is a combination of simple functions like polynomials, exponential, and sine and cosine only. Okay. So, this actually what you do is, what you have is y double dash plus px y dash plus qx y equal to some fx, let us say simple function, either e power x or sine or cosine of x, okay, or polynomial Pn of x, polynomial like say x power n. okay, n belongs to n, or combination of them. Combination means what? So you can have x power n into e power x into sin x or cosine x, like that. Okay, you can have any kind of forms, any combination of this, either two of them or some of them, like that. Okay, you can have x power n e power x cos x also. So you can have like this. When the right hand side is in like this, you say it's combination. So in such cases, what we can do is you can find a solution. Okay, so what we do is a method of undetermined coefficient means you look for certain form. Okay, when you are, suppose these functions are given as a constants, some, let us say a, and this is b, a, b are constants. Okay, a, b are constants. If you are given some constants, you look for some, if your right hand side is e power x, you look for some form. So assuming yp of x is some form. So depending on either this, when the right hand side is exponential or sine or cosine, or the combination. So for each combination, for each of these right hand side, you have certain form for ypx. For example, e power x, you just look for some constant c1 into e power x. This is how you look for your solution, and then you substitute into the equation and get your c1. You expect to find this c1, but how do you find this form c1 into e power? So you have to remember, for each combination, if you can remember the form of yp, then you can determine this constants. That is why this method is called the method of undetermined coefficients. Okay, but then in this method, you will have to remember exactly the form of the particular solution when they are depending on the right hand side. Given a right hand side involving these simple functions or their combinations, you should know exactly what is the form it has. Okay, a particular solution has. So but there is a way. So if you can remember all the different forms of yp, you can find these constants. That's why the method is called method of undetermined coefficients. Fortunately, we have a method called annihilation method. So what we do is we kill the right hand side by applying some differential equation. So because each of these functions are solutions of some differential equation with constant coefficients. So if you apply that operator on both sides, I can make right hand side 0. So annihilation method. That's why it's called annihilation method. So by killing the right hand side, non-homogeneous term, so smallest operator, you apply both sides, differential operator, you apply both sides, make the right hand side 0. Okay, and then, so annihilation methods, what I do is, so let us take some simple example, y double dash plus a y dash plus by equal to e power x. Let me give you this. So before I give you a method, maybe I should tell you. So e power x is the solution of dy by dx minus y. Okay, this is what is the solution, right? So this is the solution. So this is equal to 0. If y equal to this, then you can, this is what it satisfies. So you can write this d, which is let d is d dx, then you have d minus y. This is your operator acting on y is 0. So this is your annihilator. The square is also annihilator, but we take the lowest one, minimum. Okay, because yx is right hand side is e power x. If I operate this d minus 1 on this, right? So what is y? Y is actually e power x. It is 0. Okay. So for when you are given e power x on the right hand side, so this is your operator. You have to operate on both sides. That is d dx minus 1 minus y actually. Okay. D minus 1 means, so you can see that d dx is 1. So basically d power 1. This is d power 0, that is 1. Okay. No derivative, 0th derivative on y. So acting on this function e power x, which is y. And what if I have y is sin x or cos x? Then what is the solution? Solution is, you know already, sin x and cosine x are solutions of, let me give you in general. So if I have e power ax, a is a constant. So let me take some constant c. e power cx, c is a constant. So then what is that you have? So you have c times y. So this will become d square d minus c. Your operator is d minus c. If I have sin cx or cos cx, then what is your differential equation that is satisfied? So you have seen that when you have a solutions like sin cx and cos cx, y double dash plus y equal to 0. What are the solutions? If you are looking for y equal to e power lambda x, lambda square plus 1 is 0. So lambda is plus or minus I. So e power ix is one solution, e power minus ix is another solution. They are linearly independent. If you take sine and cosine, same way you can say sin x and cos x are linearly independent solutions. So sin x and cos x are solutions of this differential equation. Okay, so that will tell you what should be our sin cx and cos cx. So if you want sin cx and cos cx, icx, icx. Okay, you need ic. That means I should have c square. That means you should have c square here. Okay, so that should be our differential equation. So I can write d square by dx square double dash is that plus c square acting on y equal to 0. So sin x and cosines are both solutions of this differential equation. If you have a right hand side y sin x cos x, you operate this both sides so that you can make that sin x cos x 0. Okay. Similarly, if you have a simpler one, something like x square, let us say, simply take x square or in general x power n. What is that derivative? Because it's a polynomial, n plus 1 times if I differentiate, it will become 0, right? So you have dn plus 1 on y equal to 0. So your annihilator is d power n plus 1. So this is your operator, you have to operate on both sides. Now let's go back to this equation, this simple example where you have, so what you do, take this y double dash plus ay dash plus by equal to e power x. So let us apply, I want to make this right hand side 0. Okay. Before I making this, what is the solution of this homogeneous equation? So let's fix this a and b some numbers. Okay. Let's take simply 2 and 1. Okay. So what is the homogeneous solution of this equation? This is simply c1 e power minus x plus c2 e power x into e power minus x, because e power lambda x, if you substitute into the equation, you will get lambda square plus 2 lambda plus 1 is 0. That will become lambda plus 1 whole square equal to 0. So lambda is minus 1 and minus 1. So you have one solution is this, because it's a repeated root, you have x into e power minus x. So you keep this homogeneous solution. Okay. Now you operate the given equation both sides, because e power x is satisfying d minus 1, right? So d minus c is 1, so d minus 1 is the operator, dx minus 1 acting on e power x will be 0, right? So both sides I apply ddx minus 1, and then I have here, if I do operate on the right hand side, ddx minus 1 on e power x, then that is 0. Okay. Now what I got is this equal to 0. Okay. So that is, if you do this, y triple dash plus 2y double dash plus y dash minus y double dash minus 2y double y dash minus y equal to 0. So this implies, so what is this one? So this is y triple dash plus y double dash minus y dash minus y equal to 0. Okay. So you don't have to expand like this, because you already have. So this equation is actually, now you can write d minus 1, ddx minus 1, d minus 1. This you already know its expansion, lambda plus 1. So if you can write always d plus 1 whole square. If you actually operate on y, you will get this equation. This y double dash plus 2y dash plus y. If you simply look at this, we expand this d dx plus 1. So like d plus 1 whole square is d dx plus 1 acting on d dx plus 1 on y. So dy by dx plus y, if I remove, take it. Now you differentiate, this becomes, if you differentiate this, y double dash plus y dash plus 1 into this. So this is y dash plus y. So exactly that equation plus y. So if you are given equation like this, double derivatives you can put d square, okay, and then this d square plus 2d plus 1 acting on y. So that is nothing but your equation in this polynomial, okay. So that will give you, wherever lambda is there you can put d, so d plus 1 whole square. So that is what we can write like this, okay, equal to 0. So this is your equation. If you actually substitute y equal to e power x, now if I find the homogeneous, what is the general solution of this equation, you can, how do I do that? We choose like this, so that lambda satisfying lambda cube plus lambda square minus lambda minus 1 is 0. Or you can also put it here, so that will give me lambda minus 1 lambda plus 1 whole square equal to 0. If you put it here, if you put y equal to here e power lambda x, you can easily see that lambda minus 1. So wherever d is there, you put lambda minus 1. So that's what, so you will get the same, okay. So by directly, once you are you're already having this separated, so you break this, you write it as a product of these terms. So this you can write like this. You have this, so for this homogeneous equation you have the roots, lambda is 1. So you have these roots, so you can write y of x, y homogeneous, okay. So for this equation I am writing, so your so yx will be c1. So I write for these two roots, c e power minus x plus c2 x into e power minus x, because minus 1 is repeated root, plus you have third root. Third root will have c3 e power x, okay, because that is how you look for your solutions. This is your general solution of this third order equation, okay. But you don't know how to, we have not done the solutions of higher order equations. That is much similar to the second order equations. If you have this is a higher order equation, third order equation, okay, with constant coefficients. The procedure is same. You look for solutions in this form, you get a polynomial that will have roots. These are the roots. These are e power minus x, x into e power minus x, and e power x as solutions, okay. If they are repeated, you write like this, and which are different, you will have, these three will be linearly independent. We will see that, okay, little later when we do the higher order linear differential equations. When we do, we will see that, okay. So this is what you have as a general solution of this equation after annihilating the right hand term of the non-homogeneous second order linear ODE. So in this you have already homogeneous solution of the given equation. So this is your homogeneous solution. This you remove from this. So this is exactly you should look for. So this implies you look for, after removing this that homogeneous solution from this homogeneous solution, from this general solution of the homogeneous equation, okay, this solution, okay, that is this solution. So you remove this YH from this general solution. That's what I did. So then you look for YP. So your YP should be in this form, C3 into e power x. So this is the procedure. Now this you substitute into the equation. Your equation is y double dash plus 2y dash plus y equal to e power x. So if you do that, C3 e power x 2 times, if I do the same, plus 2 times C3 e power x plus y is C3 e power x equal to e power x. E power x I can cancel both sides. So what I get is 2, 3, 4. 4 C3 is 1. That gives me C3 as 1 by 4. So that implies Yp of x is C3, you can put it here. So you have e power x by 4. So this is your particular solution. So, once you know the particular solution, you know the general solution of the non-homogeneous equation, that is yh plus yp. Okay. So, that is c1 e power x minus x plus c2 x e power minus x plus yp is e power x by 4. So, this is your general solution. Okay. This is the general solution. General solution of given equation. So, this is how you can have it. You can have this method of annihilation, annihilating the right hand side, and then get the whatever, if your equation is the equation with constant coefficients, after annihilation of these simple elementary functions, you will have again equation, higher order equation with constant coefficients, whose general solution, from that general solution, get the general solution of that higher order equation. From that, all the solutions of the homogeneous equation of the given equation you remove, and whatever is you are left with, that should be the form for the particular solution you should look for the given differential second order non-homogeneous linear ODE. Okay. Once you substitute and then you compare both sides, you will get those constants. That is actually a method of undetermined coefficients. Okay. So, we will do some more problems. So, before I do that, so you have seen these are the forms, these are the annihilators if it is your solution, if right hand side is e power cx. Okay. If you have x into e power cx, what is the solution? So, it will be c square. Okay. So, if your y is x into e power cx, then what should be your annihilator? So, if you see e power cx is the solution for this. If it is repeated root, c is repeated root, c, then e power cx is one root, and then x into e power cx is another root. So, you know if it is repeated root. So, repeated root comes when you have square it. So, you have lambda minus c whole square equal to 0. That is how polynomial you will get. So, the annihilator is square. So, in general, if I have xn, you will have annihilator will be d minus c power n plus 1. Okay. The same way here. So, if you have a multiplication of x power n here, okay, then you will have this power n plus 1. Okay. And then e power x, if you have e power x, we have seen. So, that is how it is. And if you have combination, another combination you can have, that is y equal to e power ax into cos x or sin x. This annihilator is, you can guess it. So, this will be, so you can put cos cx and sin cx. Cos cx and sin cx are solutions of d square plus c square y. Okay. E power ax will be there if you have complex roots. So, that is d minus a whole square plus c square. This is your annihilator. Acting on y will be 0. And if you have, this is because x power 0 is here, x power 0, so power is 1. So, x power n if you put here, and you have to take this one. This is your annihilator, that makes it 0, right hand side 0. Okay. If your y is this general final combination, x power n, e power ax, cos x or sin x, and then this is the form. So, whatever combination you give, you can find nicely what is your annihilator. This you apply on both sides, make the right hand side 0. So, that makes it, that will give you the form for the particular solution that you can substitute into the equation, get the constants, okay, get the unknowns. So, that is actually the crux of the method of undetermined coefficients. Okay.